Cheers, everyone, and welcome to this month's Astronomy on Tap. My name is Laurent, and I will co-host this event with Jake, who will present later the pub quiz. For those who don't know how this goes, we will first discuss a few news with our speaker and a guest, a few news related to astrophysics. And then after the talk, which tonight will be about astrochemistry and the molecules of life, interesting talk, we will, during which we can ask your questions on YouTube, Twitter, Facebook, all our social media. After that, I will ask your questions to our speaker, and then we will all move to the Zoom pub to have an amazing pub quiz. After which you can talk with our speaker and our guest of tonight while sharing a beer all together. So without further ado, our speaker of tonight is Veronica Allen from the Captain Institute in Groningen. Hi, Veronica. And our special guest to discuss the news tonight is Natasha Johnson from NASA. Hi, Natasha.
Yes, hello, hi. It's not tonight, it's today.
It's completely crazy now.
Okay.
All this change of time. What time is it at your place? Okay.
Oh, it's only like 2:00 in the afternoon.
Okay, perfect.
I could have a beer, but I think my bosses would be frowning on me. So
so yeah, we can directly go to the news. And so the first one is that 58 years ago, so that's not really a news, the first woman was sent to space, and she was Russian. The name was Valentina Tereshkova. And before watching there is many interesting thing about that. Before going to space, she didn't have any experience. She was just pre-selected because she had experience in skydiving, and she's still to this day the only woman that went to space solo, and the youngest one. She was only 26 years old, and she stayed there for 3 days aboard Vostok 6, and her mission was to study the effect of spaceflight on humans, and it was a success. And after the mission, she wanted to still go to continue her career as a cosmonaut, but after the death of Gagarin, they didn't want to lose another hero, the space program, so she had to go into politics, and she was a role model for a lot of young girls. And an interesting fact is that after that, we had to wait 20 years for another woman to go to space. She was Russian as well. And then just 1 year, a few days later, so exactly 20 years and 2 days later, the first American woman was sent to space. So that's not really great for America. What do you think, Veronica?
I was actually sort of obsessed with Valentina Tereshkova as a child. I have these clear memories of maybe being 10 or 9 or 10 and someone telling me, oh yeah, Sally Ride was the first one in space. I was just actually, because I was an annoying child, actually, instead of Valentina Tereshkova, practice that name because it's really fun to say.
Mm-hmm.
And yeah, she's incredible. And I think she's still alive actually, because she was so young. Yeah. Right, when she did that, and she was an expert at paragliding or something as well. Yeah. Mm-hmm. So they were just like, well, you fit, go into space, have fun. It's incredible. And then yeah, she became very involved in getting the space program in there going, and I think she was also influential to young women. I'm sure around the world. If I was in America. I think there was a Lego set that was I think it was important women in astronomy or something, and they had Sally Ride, and I was just but Valentina Tereshkova.
Yeah, for sure.
It's so cool. Yeah.
And that's very impressive. And they I read that they also sent her because they heard that American women might go to space, and then they said, we have to go first. We have to to show them. And then they had to wait 20 years after sending another woman. So, but yeah, she was really a pioneer. Yeah. The second news is, of course, the eclipse that happened on the 10th of June. Did you follow the event?
I didn't get a chance to see it, but I saw a lot of cool photos. A lot of people took pictures. Like you can use any sort of thing with a small hole. So this has so many people using colanders. I saw someone using a cracker. That was really cool. Because the cracker with the holes in it, and you could still see the eclipse through there. But yeah, I didn't get a chance to see it, and I don't have any filters for my telescope, so it was. No, it's not going to happen. But I think it was a pretty clear day, so there must have been a good turnout.
There were some YouTube cast as well that were showing it, that would follow like Leiden, also Groningen. So there were a couple. It was really interesting to follow. But since you missed it, you might be interested in knowing that the next one is next year, actually, in December, I think, 2022. And
we can see it here. Well, maybe not. In December, near the winter solstice in the northern reaches of the world. I don't know how much sun we're going to see. Oh, okay, it's October. Okay, that's better, but still not good. we have a chance.
October 2022. Yeah, but that will be a partial one, and then after that, the first annular one, which is the one where we see the ring around, will be in 2093. Yeah, that's in quite some time. And then
be old then.
Yeah, I'm not sure. I mean, we might, who knows? And then the next total eclipse will be in 2135. So there is a lot of time.
That would be difficult. I'm going to live that long. I'm going to do
it. Yes, on to the third news, which is, I think, very, very interesting. I mean, when I read about it, I was quite surprised. It's about Twinkle, which is a satellite that is going to be launched in 2024, and it's going to be launched by the company Blue Skies Space. And the interesting thing about it is it's from a postdoc at the University College London, which wanted to study exoplanets, and he made a proposal, and it was rejected, and it happens a lot. And then he decided that he would make his own satellite to observe exoplanets, to really focus on them, because so far we had Hubble and some other telescope that could look at identify exoplanets, but couldn't really study them, and he wanted to really study the atmosphere of exoplanets. And so he decided that this system of the big telescopes being controlled by government-funded agencies, and that took decades. I mean, we know about JWST, right? That take decades to be launched and billions of dollars. He was like, no, I'm gonna make my own, and I'm gonna fund it through private funding, so by universities that can pay. And the universities will subscribe to the satellite to get access to the data, and they want to through that to make enough money to get the cost back from the satellite and start building a second one. And that would really be a whole new way of doing space science. And he said that the worst thing was that, so the scientific part was not the problem. The problem was the skepticism of the scientists that didn't believe in this model, is this new way of doing things. But after a lot of conference, he managed to get a lot of backers, and now this satellite is going to be launched in 2024 to study the atmosphere of exoplanets, so the presence of water or carbon monoxide. So I have to say that it's quite impressive to decide to make your own company and change the system like that.
I suppose if the subscription model works for Netflix, it can work for anything. But I don't know, that gives me mixed feelings. Sort of, it's nice to have small projects. I know that CubeSats are a thing, so the small satellites that they send up. Mm-hmm. But also, I think science should be open, completely. So this yeah, it gives me weird feelings. But it's certainly an interesting new development. Yeah.
And I wonder if that's going to set the path for the future. And because it basically compared it to SpaceX selling rides to the ISS, and so he was like, yeah, we're just going to sell scientific data, which is kind of edgy, selling scientific data, but that was the idea, and it's working. I mean, they're gonna launch it, so it's quite impressive. And for the last news, it's quite excited. It's quite exciting. Sorry, it's about the 2 new missions that are planned to go to Venus. And we are lucky to have Natasha Johnson with us, which is in charge of one of the mission, and will tell us. Oh, with a nice background, will tell us a bit more about it.
Oh, can I talk now?
Yes.
So yes, hello, hi, I'm Natasha, and I just wanted to say hello, and I'm the project scientist for Da Vinci Plus. Now, just recently, we had Veritas and Da Vinci selected to go to Venus, and this was just selected a couple of weeks ago. So this is big news, and we were only expecting one mission to be selected. Just so you know what it is that we have NASA selects missions from time to time, and this is one of the ones that had been selected for the Discovery missions, which tend to be lower cost. And typically they usually maybe select one, but we were amazed that they selected 2 because the US has not been back to Venus in over 30 years. Magellan was the last time, and that was a radar mission. And so the one I'm on, I'm a project scientist, and the one who's actually in charge of it, I'm the one who talks to the scientists and the engineering team, is the principal investigator who actually controls it and steers the ship, right? So anyway, so what we are is a probe. So we're going into the atmosphere. Now, the Russians were incredibly successful with this, the Soviet Union, back in the 70s and early 80s to get composition data. But since that time, we haven't been back, and we're going to throw a mass spectrometer in there, a tunable laser spectrometer. The other mission, which is run out of JPL, Da Vinci's run out of Goddard, which is a NASA center in Maryland, and JPL, which is down in Southern California, they're running something called Veritas. And it's supposed to be truth, and it is actually an acronym, as is Da Vinci. Don't ask me what it means because too many words. But what that one is an orbiter, and it's supposed to look at the topography, whereas Magellan looked at the surface roughness. Veritas actually looks at the elevation, and it's going to be looking at the infrared. So it's going to, in combination with Magellan, hopefully we can find out more about the morphology and some of the, the geology or the actual changes on the surface. Like, could there have been volcanism? Well, there is volcanism, et cetera, et cetera. But the other big thing is that Envision, which you guys have heard about, that was also selected. So this is the Decade Venus. It's not Mars anymore. Okay, sorry, I'm stuck in the planets. You guys are in the stars. Okay, and we circle your stars, so we're related. But so that's what we do. And so this is really amazing because we did have Venus Express, which was run also by, I believe that was also an ESA mission. That was just recently, but that was a huge orbiter and very, very accessible. And I think that's one of the reasons why they thought, okay, we're getting this culmination, or there's this impetus to go forward with Venus. So so Veronica called, and, we had worked together. And so I was like, yes, I would love to come and join you guys. And I would love to have a beer, but I cannot yet. I have to wait 4 more hours. I could, but my work then I would have to work in the night. I don't want to do that. And I'm distracting you folks. So anyway, so that's Da Vinci Plus. Yeah.
We're delighted to have you with us. When are the missions expected to launch?
Oh, well, fancy you ask. Yes, no, it's supposed to be, so the 2 missions, Veritas will go first, and it's scheduled to launch now in 2028. And then Da Vinci is expected to launch in 2029. What's good about these Venus orbits is that it's very short to get there. It only takes about a year. I think we were actually we were hoping to go earlier, but I think just because of mission delays and scheduling, that's why they pushed it out, and also funding, et cetera, et cetera. So, so we're in 28 and 29. So
okay.
that's
we'll make sure.
Yeah. So try not to think of my age. Yes. Right. Yes.
Do you might stay after Veronica's talk and join us in the Zoom pub to talk more about these 2 missions? or do you have to go back to work?
I probably do have to go back to work, but I will stick around for a little while, and I'll keep you. You're on my personal computer at the moment, so I'll keep an ear out.
Oh, perfect.
Can,
Thank you very much.
yes.
And we will make sure to talk with you after the talk.
Thank you for having me come along. I'm very, very happy about it. So chuffed, as they say. So,
okay,
so thank you very much.
In the Zoom pub. Ciao. Then I guess we can move on to the talk. So Veronica will tell us about astrochemistry and the molecules of life.
Okay.
All is set.
I got to go to full screen, and it all looks good, yeah?
Perfect.
Okay, so I'm going to tell you a whole lot about sort of how this science works, what the background is, and like what I think I'm going to do with it. But here we go. Also, I started drinking like an hour ago, so apologies if it gets weird. Here we are talking about the origin of life, and everybody loves that. There's not anyone who's not interested in like where we come from. Well, I'm sure there's someone, but where did life come from? How did it start? Because that's not a solved question. There's a lot of ideas and a lot of leads onto like how life developed on Earth. But from the like sort of astronomical external to Earth point of view, it's generally thought that these prebiotic molecules, which is the ones that lead to biological molecules, so they're prebiotic, they formed in space and were probably delivered to a young Earth to kickstart biology. So this is the big question: where did these molecules come from? So you really need to know a little bit about molecules in space. And you may be surprised to know that molecules form in space, but we have kind of a limited stock cupboard for our molecules. This is what people refer to as the astronomer's periodic table. And you can see there's a lot of stuff missing, and there's a giant H here for hydrogen, because like it's mostly hydrogen and then some helium, which is not super useful in astrochemistry. I hope nobody who's studying the formation of water comes after me because they think that's important. But yeah, and then you have like mostly hydrogen, and then some C, N, and O, which are also important. And there's 6 elements that we think are important to life that we find in like amino acids and proteins and things. And we give them this acronym. Well, it's not really an acronym. It's the letters for all of the elements, and we call it SHNOPS because that's fun to say. And it's, you know, carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur. And you can see that my image credit here is Olivia Harper Wilkins, who's a PhD student at Caltech and one of my collaborators and a fantastic artist. So this is like sort of my really terrible illustration of how chemical reactions can work. So molecules that are in the gas form can stick onto dust grains. So that literally like almost like sand grains hanging out in space in gas clouds. Gas and dust clouds. And when they're cold, like these atoms and molecules in the gas can stick to the dust, and then we just call that ice. Everything that's stuck to the dust is ice. There's obviously water ice, but there's also carbon monoxide. There's also these guys, HNCO. This is my friend formamide. So that's one way to make molecules in ice. But you can also make them in gas. So like obviously there's a lot of gas in space. If you see a nebula, that's all gas, more or less, and some dust. And the reactions can happen just in the gas if it's warm enough for atoms to meet. But there's not a lot of stuff in that gas. It's very low density. So it can take a really long time for any 2 atoms or molecules to meet in space, which means that the reactions are really slow. But there's a whole lot of them. So that's how we know that chemistry can kind of proceed. It can kind of go because the reactions happen like once every 10,000 years, but there's 100,000 molecules. There's actually way more than that. But yeah, and so they have this chance of reacting, and you get like 10 reactions a year or something like that on average. It's all statistics, which I should have taken in high school. So what else is important is one of the cool places to look for chemistry is in star forming regions. So stars form in these gas clouds, gas and dust clouds, where it's cold, and the chemistry in the cold time is different than when it gets warmer. So in the cold time, you have slow reactions taking place on the ice and in the gas, and it's just sort of all very slow, and very nothing that requires energy to have a reaction. So like some things you have to add, like if you're, if it works the same as cooking, you have two things in a pot, and if you don't heat it up, there's no change. So some things require heat or energy to change. As the cloud starts to kind of fall in on itself, gets smaller and denser and hotter, then you get some of the molecules that were made on the ice can leave and go into the gas and react there, or just hang out, and we can see them. And this is a really cool like time in a star forming time, as a star is forming, because you get all kinds of really crazy molecules, like ethanol, which is alcohol, and some molecules, not necessarily biological molecules, but things that lead to these prebiotics that lead to biological molecules, and we call these things, which are in this stage of formation, hot cores. So they're cores because that's what we call the things that are forming stars, and they're hot. But hot actually means like 300 Kelvin, which is like what, 30 Celsius. Not hot to us, but hotter than cold, which is 10 Kelvin. So that's what hot means. It's all relative in astronomy. Once you get the star to actually form, then it gives off some like UV, because stars, when they form and make energy, they give off high energy radiation, and they can form a planet forming disk. They certainly generally form a disk, although this is sort of argued about in the study of stars, which are much larger than our sun. But there's the gas and dust starts to thin out or become planets or get blown away, and there's more UV. So there's even another new time for chemistry here, where you get a lot of energy thrown into the molecules and have new reactions, but they can also be destroyed because there's no dust to protect them from the UV. They can just like have so much energy that they come apart and become smaller things. And then if you're lucky, you get a planetary system. There's no necessarily proof of planetary systems much larger than the sun, in stars, much larger than the sun, but you never know. So like that's where the molecules in space come from. The cool thing about like trying to study these prebiotic molecules is that we know what we're looking for. In a way, we're looking for molecules that have N connected to C connected to O, this chemical bond. So it's like nitrogen, oxygen. And my friend formamide is one of the biggest that people are studying right now, and it's my biggest interest as well, because it's been shown to lead to the simplest amino acid, glycine. So I'm sure you've heard of amino acids because like ads on the TV tell you that they're important for something. And I'm not a biologist, but I believe they have to do with the formation of proteins in the body. In any case, they're very important biological molecules. And so I've got little formamide here. It has an NCO, so you can see kind of like what that looks like. And it's actually surprisingly easy to study formamide because it's basically everywhere. I think a child is coming. Oh yes. Bear with me. Right, you can stay if you be quiet, or you can go watch TV. You get to choose. You want to play? I can't play. You can't play Super Mario here. This happens sometimes. I'll keep talking. I'm not in charge of that. Glycine, on the other hand, has only really been detected in comets. And there was a disputed detection of glycine in interstellar clouds, like where like stars are forming, but it's not been detected for sure. So we know that this formamide can lead to amino acids, but we don't see the amino acids, so we don't really know what's going on there. So we need to know how the formamide was formed, like where did that come from? And then how does it survive long enough to be delivered to like an early Earth to kickstart biology, as I said. So there's like, I use 3 techniques. There's more techniques. There's a lot that happens in astrochemistry. And so I use observations of gas, and I intend to use observations of ice. And I also use what's called chemical modeling. So all these things together can help us understand where these molecules come from. And then eventually kind of stick it to how they got to Earth and how that kickstarted biology. So to observe gas chemistry, I use this cool observatory called ALMA. It's my favorite observatory, and they know it. I'm a big fan. I would love to go there. It is, that's an acronym for the Atacama Large Millimeter Submillimeter Array, because the wavelength range is in millimeter and less. So it's in the Chanantor Plateau in Chile, which is great. I'm going to show you. There's like, it's a really high mountain, and there's these cute animals, and one of these is called a Vicuña, and one of them is called a Vizcuna, and I can't never remember it's the llama thing or the chinchilla thing, but they're super cute, and the Alma Observatory has a very active social media presence, and they like to post up their little animals. I don't even remember what this adorable fox is called, but I love his face. Right, so that's it. That's Chanantor in northern Chile, in the middle of nowhere at an elevation of 16,000 feet or 5 kilometers. And so it needs to be at this high altitude because there's water in the atmosphere, and the water basically blocks out all of the good stuff, all of the cool molecules that we want to see. It is 66 of these dishes, all like tied together, basically like with cables, not like with string. And they work together so that they can detect weak signals. There's a really good description that said, like, it's like if you had a bucket, you could only collect so much rain, but if you had loads of buckets, they're not any bigger, they're all the same size, you could collect like loads more rain because you had more collecting area. And that's how the dishes work. They collect lots of light. And so you can see like these gases that are very, very low abundance. So they're not a lot of them out there, and you can still see the signal from them. The wavelength range is useful to detect molecules rotating. So like as they rotate in space, they give off energy, light particles, photons, that is very low energy, but it's the right kind of energy to be detected by these telescopes. So we just see rotating molecules, and this means the like resolution of the pictures. So this is really small, and this is not so small, but both are useful, so that you can see like local changes in the chemistry. So I can show you what actually the data looks like. This is some of my data. This is a molecule called methylformate. And this is just like the gas, the bright bits, the right rainbow bits are where the brightest, the hottest or strongest lines, the strongest, it's sort of the most amount and the highest temperature together of this molecule are at any given speed. So this is like, you can see the motion basically. The speed keeps changing. So you see the molecules, the gas moving in like, it's meant to be in like a disc-like shape. So we can see a lot of stuff about the regions that I'm studying using this kind of maps and spectrum data. So the idea is I'm going to look at lots of different types of young stars that are forming to see how like the environment changes how much of the molecules that there are. So like a smaller star will have a lower temperature and lower amount of UV coming out. And a larger star is hotter and it has more UV coming out, and it also forms faster. So you have less time for chemistry to do its thing. So that should be interesting when it's done. So we need ALMA, and it's awesome, and I have data coming. The other thing we need is this to observe ice chemistry is James Webb Space Telescope, which I swear will launch probably. I hope. And it will be able to observe the molecules in ice. So molecules that are frozen, they're stuck to the dust grains, they can't rotate. So we can't see them with ALMA. So instead, you see the vibrations of this, like the atoms within the molecule moving relative to each other. And that is in the infrared, which is what James Webb uses. And so you get this crazy looking spectrum, this is like squiggles, right? But each of these squiggles means there's this molecule there. So like you get your spectrum from James Webb, and it'll have all these squiggles, and you go, aha, there's CO2, awesome. And the XCN is actually an important one for these molecules with the NCO bond. So that's going to be really exciting. It's much more powerful than the last infrared telescope, space telescope, which was Spitzer. And so we can learn about what kind of molecules can be made on the dust grains. Because it hasn't launched yet, we don't have new information, but we expect to have lots of new data next year that will show like all the different cool things in the ices. And so the least exciting part of my work is chemical models, but I've put in some pictures so that it's not like soul draining. So a chemical model uses the formation rates, right? So what the chemical reactions you need to form different molecules and the ones you need to destroy different molecules. And then you do that, and you know how often that happens, and then you say runtime, and then you have like, oh, this happens every 10,000 years, but I have 100,000 particles, it happens 10 times or whatever. But it does that for like hundreds of different molecules and thousands of reactions, so we times this by thousands. So it's got a lot of input data. And then we put in like the temperature. So we say, oh yeah, this is a higher mass star, it's got a high temperature. The density, which I've chosen like this square to represent. My husband said to use bread, and I was like, nobody's gonna get that bread is dense, so I didn't. Now we have a square. Temperature and density and UV to figure out how those things affect the chemistry that happens. So all this goes into a nice computer. It does a thing, it comes out, and it shows you what the composition of whatever you're looking at is at whatever time you want to look at. So basically you're like, how much ethanol do I have? And it goes, this much at 20,000 years. And that's it. Okay, cool. I can compare that to observations I did and then figure out if that's normal because theory is funny. So basically, I have to create lots of different environments and see what happens. Basically, I'm going to make like 1,000 environments and see which one looks coolest and like which one forms molecules that I'm interested in, the prebiotic molecules, over how much time and things like that. So wrapping it up, bringing it all together, we got ALMA and gas, molecules in gas. We got JWST and molecules in ice. We've got, this is literally my computer showing a picture of astrochemistry, but it's going to do the modeling. And I put it all together, and it's me. I also bake and sew. And then eventually that will help us figure out like how molecules of life got made in space to hopefully, in theory, kick off life on Earth and maybe somewhere else. And that's about it.
Thank you very much. That was super, super interesting. And maybe you will give us the key to how we got there.
I hope so.
We had a few questions from our viewers. The first one is it possible to estimate how often formamide is transported to planets, so whether this is really likely or really unlikely?
Oh yeah, it is actually, I think it's found in meteorites. There's some people that I know who studied meteorites, and you can find it, and like actually amino acids and like actual real prebiotic and biotic molecules. And so I know someone else who studies like the delivery of particles to planets. So it is, I don't know how you calculate the time, what's it called, frequency?
The rate.
But yeah, the rate, yeah. But like I'm sure that's possible to calculate. It is, it's ubiquitous. This formamide is everywhere. You see it everywhere. And so it's really likely that it's within the material that falls to Earth all the time, and so could have done so in the past. I don't know how much you would need to like actually get started with biology, and I also don't know a lot about the like delivery process. I believe you know, meteorites, if they're big enough, the stuff that's inside stays unaltered deep inside, and so you know, you form if you're forming meteorites, like you have these dust grains which have these ices on them, which could have these molecules in them, but they get compacted with other dust grains, and the ices may stay inside. So like it's not like they all transfer to the outside. That would be ludicrous.
Right.
Yeah. So they would be within, and it's entirely likely that that is possible.
It might be likely. Yeah. It might be likely, but that doesn't necessarily spark life. Or
I imagine you need a certain amount. The experiments that were done to turn formamide into glycine, where I think that he tried to simulate the conditions of early Earth. So like, what was it? Was it high oxygen or high carbon dioxide? I can't remember. Was it high carbon dioxide? Because the trees were bigger. I don't know the specifics. I'm not a biologist. I'm barely a chemist. But yeah, you would need probably a certain amount. And there was obviously in the early period of Earth, there was a bombardment. There was like constant stuff being delivered. So it's you know, it could have been delivered at that time. That's something for like a much later part of my research. I have like a very long plan, and it starts with space and ends with Earth, except I don't know a lot about Earth.
That's very interesting, because the second question is, do you also work with chemists to research, so first, possible reactions in space, and second, how to test these processes, so how the molecule form here on Earth?
Yeah, so actually that is also a big part of my project is collaboration. For me, like astrochemistry is this huge collaborative enterprise, just to copy Carl Sagan. We need the modelers, we need the observers, we need the experimentalists, we need all of them. And because it doesn't work without, you can just like make stuff up, be like, yeah, I modeled this, it's true. But without observations to back you up, then you're like, you modeled this, but like, I've never seen it in space, so whatever. Or, you know, or they can't make it in the lab, so whatever. So yeah, I have some friends who do laboratory work, who should we get funding for them to do this project, like they're going to help me by doing some lab experiments to try to form formamide. On Earth, you can sort of simulate space, but the problem is that the vacuum is the dense areas of space that I study are much higher vacuum than like the ultra high vacuums machines that we have here. Wow. So like the best vacuum on Earth is still like really dense for space. And then because these reactions are slow, they tend to be done at a higher temperature, so to speed them up, and then you extrapolate down to low temperatures. So this is not necessarily like exactly going to be right, but it's sort of the best we can do.
You do try to combine theory and practice.
It's super important. Sometimes the people in the different sort of categories can become elitist for their own category, and I don't like that. I know how much we're intercombined, and we need to work together. And so there's no reason to say, oh, but those models weren't completely perfect because they didn't take into account X. And you're like, okay, but that was the best we could do, because have you seen computers? Like, computers are amazing, but there's only so much time in your life when you want to run a model, and you want to add everything, it's going to take like the rest of your life. So you have to approximate some things. And I don't like when people don't appreciate that. So yeah.
Great. Interesting question. What would be the most interesting results that you would like to discover?
I want to find some new prebiotic molecules. So they're actually, formamide has been studied a lot recently in the last maybe 10 years. It's been really popular. And we haven't really figured out how it forms, but they've also in that time discovered 2 more prebiotic molecules, but only in 2 places. So I want to find a new one. I want to find another one. There's so many prebiotic molecules, and there's so many ways that amino acids can be formed. I knew someone who was studying the formation of the DNA base pairs in space. I'm like, if you can spontaneously form DNA base pairs in space, like, yes, that sounds awesome.
Yeah.
So I would love to find something that leads to that. That would be awesome.
It sounds crazy because it's very complex.
Yeah, well, if you give it enough time, you'd be surprised what you can form. These really low mass stars, they have a low temperature, but they're like slowly heating up, slowly adding energy for millions of years.
Yeah, the universe,
yeah,
the whole universe gives you enough time.
yeah, it's possible, but it might not be possible to be detectable.
Have these molecules been detected on the planets in the solar system?
You know,
or maybe it's going to be the missions to go to Venus.
I don't know if they get messed up on Venus. I wanted to look for them, but so Titan's this big place to look for new molecules, but it tends to be nitrogen molecules without oxygen. So formamide has got both. The oxygen, I think, on Titan is meant to be locked up in this the water ice that's frozen, like permanently frozen. And so it's not available for reactions.
So it might be
like it might be there, but it would be locked up down like below the methane seas. Oh God, all the children are crying.
Yeah. It's the joy of working online, right?
Yeah. And then like the gas giants like don't have a lot of really complex molecules. It might be on Mars, but I haven't read anything about it. Everybody likes Mars, but for me, the Mars is like the popular kid, and I sort of avoid it. I'm just like, you popular kid, I'm not going to study you. You can, everybody else can study you.
Yeah, so
it's too popular.
So as a last question, I don't know if you can really answer it. Would coronavirus survive on Venus? What's your opinion?
It's really hot there. Probably not.
Probably not.
I thought heat destroys it. Heat and UV destroys it, right?
So I guess so. Actually, we wouldn't be able to survive, but so the coronavirus.
But neither would the corona. Yeah. Yeah.
Thank you very much. We will see you in the pub quiz, where our viewer will have a chance to try to defeat you and make more points. So see you in a few minutes there. To enjoy this beer. Ciao, ciao. Ciao, ciao, Natasha. Oh, wow. Hey, Jake. So we will, sorry. We will see you guys in the pub quiz in a few minutes. Jake is gonna put the link soon.
The link's been there for a while. But now the entire team wants to say happy birthday to Laurent. Come say happy birthday to Laurent in the STEM pub.
Come say happy birthday to me, guys, in the Zoom pub. See you soon.
And yet, everyone else, now Laurent ran away. Please come to STEMU/Zoom pub and we will do the quiz in there in a few minutes' time. Please join now. We'll stop the stream here, wherever you're watching it. And you can see the quiz in our Zoom pub. Thanks for joining us tonight. And please come do the quiz, hang out, and say happy birthday to Laurent. Otherwise, see you next month. Bye.